Good morning. So this is the last week of lessons for pre-calculus. Just a quick reminder, if you're a senior, you're not doing this part. Just make sure you have week 3 turned in, and then you should be good to go. So section 14.3 is called binomial probability. So the first thing that's going to be really important is we understand what a binomial experiment is. And what gets really interesting with these is what happens when we look at multiple of these binomial experiments happening together. They create what's called a binomial probability distribution, and we can use this to calculate things like, what's the probability of flipping a coin 4 times and, doing that, flipping that coin 4 times and getting, 2 heads or something like that, where that was really difficult for us to do without this binomial probability. It's actually going to be really easy to do now that we've talked about this. So the very first thing we got to talk about is what is a binomial experiment. And so a binomial experiment, very simply, anytime you see the prefix bi, that's going to have something with 2. It's an experiment where each trial has exactly 2 outcomes. So a classic example would be flipping a coin. You've got heads and tails. But anytime we can write something so that it has a thing we want to happen and a thing that we don't want to happen, those can be 2 outcomes. Because it doesn't really matter whether or not these 2 outcomes are equally likely. So heads and tails are equally likely. That's going to be kind of the simplest case. But we could also look at something like rolling a 1 versus not rolling a 1. They're not equally likely, but it's still just 2 outcomes. We can group all the other not ones together and make this as just 2 outcomes. So it's a binomial experiment. And so anytime you can write something as this thing either happens or it doesn't, that can be a binomial experiment as well. So we're going to take a look at one example here, kind of what this looks like without the binomial experiment. This is the one I just talked about. And we're not going to do it this way because this is obviously really annoying and takes forever and isn't even possible on a lot of the ones we're going to talk about. But we're going to look at how many different ways you can flip a coin 4 times. And then what is the probability that you get exactly 2 heads? So this was actually pretty similar to one you did in your homework. And so if you remember in the homework, when we flipped that coin 4 times, we had possibilities like heads, 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 heads. We could flip that coin 4 times and get all heads. Or we could flip that coin 4 times and get all tails. We've got, those 2 options. But we've also got options like heads, 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 tails, or heads, heads, tails, heads, or heads, heads, tails, tails. And we can keep going through these. And if you remember, there were a total of, I believe, 16 of these. And probably the hardest part was just to organize these. So if I went heads, tails, heads, heads, and then heads, tails, heads, tails, heads, tails, tails, heads, and heads, tails, tails, tails. And then this next group, you'd have tails, heads, 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 tails, heads, heads, tails, tails, heads, tails, heads, and tails, heads, tails, tails. And then our last column, you'd have something like tails, tails, heads, heads, tails, heads. Wait a minute. Make sure I get that one right before I do it. I'm just trying to match these up so that they're exactly the same, but with the 1 changed. So these all started with, you can see how these all started with tails, heads. Now I'm going to start these with tails, tails, heads, heads, tails, tails, heads, tails, and tails, 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 heads. And so you can see just getting all 16 of them listed out is going to be very, by far the more difficult part. So if we wanted to answer this question now, what's the probability of getting exactly 2 heads? We could just go through and count. So there's one with 2 heads. 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 And there's one with 2 heads. So that is a total of 6 out of our 16, or 3 out of 8. And that was a pain in the butt to figure that out. You can just imagine if I ask you a similar question with flipping a coin 10 times. There's over 1,000 possibilities there. We definitely don't want to be doing that. So let's go through. This part here is just going to talk about where the formula comes from. And we'll get to the formula on the next slide here. So the first thing we have to realize is that there are 4 choose 2 ways to flip a coin 4 times and get 2 heads. Now, if you remember 4 choose 2, that was what that looked like was 4 factorial over 2 factorial times 4 minus 2 factorial, which would be 4 times 3 times 2 times 1 over 2 times 1 and 2 times 1. So 4 minus 2 is 2. And then you see the 2 and the 1 cancel out. The 2 would cancel out there and make that a 2, and that ends up being 6, which is exactly what we got. When we counted them up in real life, there were 6 different ways. What's happening here is we're just choosing the places for those heads to be. We have 4 spots, and we're choosing 2 of them to be heads. And the reason we're using a combination is because it doesn't matter whether, as long as there's 2 heads here and here, it doesn't matter which head came first. That kind of doesn't make much sense. We're counting the order that they're in, but it doesn't matter whether this heads is here and this heads is here or those 2 heads switched. Hope that made sense. But it's a combination. We end up with 6 different ways. The next step of this is to look at how probable is each of those individual ways. How probable is it that this is the specific outcome? How probable is it that this is the specific outcome, or this, or this, or this, or this? Now, you might be able to kind of figure that out. There's 16 outcomes. To get this exact outcome, there's a 1 out of 16 chance. But let's look at this a different way and see if we can figure out why that is. If I specifically want to get, let's do this one, this tails, tails, heads, heads. What's the probability that that specific outcome happens? Well, we can calculate this because we know the probability of each of these 4 spots. The probability that this one is a tail is 1/2. The probability that this one is a tail is 1/2. That this one is a tail is 1/2, and that this one is a heads is 1/2. And the probability that all of those happen in that order is independent events. So a half times a half times a half times a half is 1/16. Oops, 1/16. Which is what would make sense. There's one of this exact way, 16 possibilities. We could do the exact same thing for getting something like heads, tails, tails, heads. There's a half, 1 out of 2 there, 1 out of 2 there, 1 out of 2 there, 1 out of 2 there. So overall, a 1 out of 16 of getting this particular one. And again, there's 6 different ways that could happen. So 1 out of 16, 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 all put together, that makes 6 out of 16. So all we're really doing here is we're multiplying the number of ways that one of them can happen by the number of ways that it can happen, or the probability that one of them happens by the number of ways it can happen, which we saw was 4 choose 2. And so in our case, what we've basically got here, and I'll explain why this is. We've got our 1/16 times 6, which gave us our 6/16. Now what this is this is showing the number of heads and the number of tails. So each of the heads, there were 2 of them in our case, had a 0.5% or 0.5 chance, 50% chance, and there were 2 of those. Each tail had a 50% chance, and there were 2 of those. And so our final expression here is going to be that we're going to take 4 choose 2 times 0.5 squared times 0.5 squared. And what these pieces are telling us, this part is telling us how many ways what we want to happen can happen. That was our 6 different ways. This is telling us the probability of 2 heads, and this is telling us the probability of 2 tails. Now, where this gets really nice, if it was always just coin tosses 50-50, it wouldn't be that bad. But where this gets really nice is what happens if we have something like a cheating coin, a coin that doesn't have a 50-50% chance. So let's go back and let's just say that the probability of getting a heads was actually 60%, and the probability of getting a tails then would only be 40%. So what we could do there then is just replace these. The probability of getting our heads in that case would be 60%, 0.6, 0.6, and the probability of getting our tails, or not a heads, would be 0.4 and 0.4. And so what that would change is that the probability of each of these would not be 1 out of 16 anymore, but they would all be the same as each other. So if you take a look here, I'm going to go ahead and erase these real quick. The probability of getting heads, just like we said, was going to be 0.6, and that heads is 0.6. And then the tails would be 0.4. I want those to be red. 0.6, 0.6, and then our tails, 0.4, 0.4. It doesn't matter which order these are in. There's still 2.6s because a heads is going to be 60% chance, and there's still 2.4s because the tails are 40% chance. And so what that would change here, there's 2.6s and 2.4s, but there's still 6 different ways that can happen. And so the only thing that changes in this formula is that for this one, we get a 0.6, and this one we get a 0.4. And now we can calculate the same probability with a cheating coin, or an unfair coin, I guess is the technical term. So the formula that we have for binomial events, and this is the probability of an event A happening R times in N trials. So in our example, the event A was getting a heads. We had the heads 2 times, R would be 2, in N trials, N would be 4. And so what we've got here is N choose R, so it was 4 choose 2 in our case, times the probability of that thing happening to the number of times we want it to happen, times the probability of that thing not happening to the number of times we don't want it to happen. And what you'll notice here is these two things, the R and the N minus R, always have to add up to the number of times you want that thing, you're going to do that thing. So if we're going to flip a coin 4 times, squared, squared, or 3 times, 1 time, they always have to add up to the number of times we're going to flip that coin or roll that dice. The probability of that thing happening and the probability of that thing not happening always have to add up to 1. If it's going to be 50% that it happens, it's got to be 50% that it doesn't. If it's going to be 90% that it happens, it's got to be 10% that it doesn't. Now, you could just go ahead and type this formula into Desmos for any particular example you wanted to. But there is going to be a little shorter way. I'll show you how to do that. So here's our example. You roll a die 10 times. What? That makes sense. Yikes. We're going to go with what are the probabilities of getting some number of ones? So what's the probability of getting 0 ones? What's the probability of getting 1 1? What's the probability of getting 2 ones or 3 ones? All the way up to what's the probability that you get all 10 of them as ones? And so the first question you got to ask yourself, is this a binomial experiment? Are there only 2 options? And even though you have a die has 6 sides, this does just have 2 options. It has we get a 1 or we don't get a 1. And the probabilities of that are going to kind of be based off of that. The probability that we get a 1, which is our probability of A, is going to be 1 out of 6. The probability that we don't get a 1 is going to be 5 out of 6. And then for each of these different cases, we're going to have a different number of ways to do that. The number of ways to get 0 ones out of 10 chances is 10 choose 0, which happens to be 1. The number of ways to get exactly 1 1 is 10 choose 1, which is 10. And we're just going to multiply those by our 1/6 to the 0 power and our 5/6 to the 10th power. Again, this 1/6 is representing the number of ways that this thing can, or the probability this thing does happen, to the number of times that it happens, times the probability that it doesn't happen, to the number of times that it doesn't happen. The 1 represents the number of ways that it can happen, which is where the 10 choose 0 came from. But let's go ahead and make this a little bit easier. So we've got Desmos to help us out with here. So on Desmos, if you go into the little keyboard and click on functions, under the distribution tab, you've got an option for binomial distribution. Go ahead and click on that. And if you look right underneath here, it's going to say that it wants the number of trials and then the success probability with a comma in between. So we were going to do 10 trials, and our success probability is 1/6. And I can actually just type in the fraction 1/6 there. And what you're going to see, when I hit this little plus sign, it's going to zoom automatically to my graph, is the probability of each different outcome. So the probability that I get 0 ones is right there. It's 0.1615, 16%. And if I actually went and just typed this in, and choose 0 times 1/6 to the 0 times 5/6 to the 10, says, no, you cannot do that. Why does it say I cannot do that? The C function is not defined. Okay. Gotta type it in this way, don't I? NCR 10, 0. There we go. So right there, 0.1615, 16%. And so all this is doing is just doing that formula for you over and over again. If I want the probability that I get exactly one, that's right there, 32%. If I want the probability that I get exactly 2 ones, 29%. The probability that I get exactly 3 ones, about 15%. And you're seeing this is going to go way down, and that kind of makes sense. The probability that I get 4 ones, 5%. The probability that I get 5 ones, now I'm down to 1%. Getting 6 ones, I'm way down there. That's actually 0.2%. Probability they get 7 ones, 0.02%. Probability they get 8 ones rounds to 0. 9 ones also rounds to 0. 10 also rounds to 0. Now, these aren't actually 0. They're just rounding to 0. There's obviously some chance that you flip or roll a dice 10 times and get all ones, but it's very, very, very unlikely. Now, what's even better here is I can use this graph to calculate cumulative probabilities. So if I wanted to ask a question like, what's the probability that I roll a dice 10 times and I get between 2 and 6 ones? I can check this box here and just set that my maximum or my minimum is going to be 2 and my maximum is going to be 6. And you'll see it adds them all up. So the probability that I roll a dice 10 times and get between 2 and 6 ones is 51%. And it's even showing you that in the graph here. What that looks like. It's just adding up the heights of all of those. So let's go ahead and answer some questions here, and then I'll show you what you're doing for your homework. So we want to calculate the probability of rolling a die 10 times and getting a 1 less than 4 of them. And so in this case, I'm going to kind of treat this like we didn't just do this exact example. What you want to consider is, step 1, is this binomial? Well, I'm either getting a 1 or not, so it's binomial. What's the probability of that thing happening? 1 out of 6. Oops, sorry. What's the probability of that thing happening? 1 out of 6. What's the probability of that thing not happening? Which I don't actually need for Desmos, but good to think about. Well, that would be 5 out of 6. And I'm rolling this 10 times. That's my number of trials. So when I go to Desmos, I have this typed in already. 10 times, the probability of it happening is 1/6. And I want less than 4. So I'm just going to type in 0 as my minimum and 4 as my maximum. And so the probability that I roll a dice 10 times and I get less than 4 ones is 98%. It's almost always going to happen. Now, if you think about that, that makes sense. You'd expect, only to get a few ones at the most when you roll a dice 10 times, because that each of those ones, there's 6 options. Out of 10 times, I wouldn't expect more than 1 or 2 ones. And so the chance that I get less than 4 is really, really high. Now, another thing you want to notice here is you can also take a look at what's the most common outcome. And it turns out 1 is the most common outcome. If you're rolling your dice 10 times, well, there's 6 options. The chance that you get even 2 is not quite as good as the chance you're going to get 1. If we change something like, if I made this 12 times, what would you expect the most common option to be? Now it's 2. 1 out of 6 chance, 12 times, you'd kind of expect that 2 is the most common option. And it turns out that it is. Okay, I'm going to go ahead and hide this one because our next one's different. Okay, a little bit more interesting here. Steph Curry makes 40% of his three-pointers he shoots. What is the probability that he makes at least 8 of his next 10? So again, our first question is this binomial? The answer there, yes. Either makes it or he doesn't make it. No other options here. So our probability that he makes it is what we want, 40%, 0.4. Our probability that he doesn't make it, well, that one's going to be 0.6. And again, we're doing this 10 times. So when we go to Desmos, we can go in and find our binomial distribution. Minimize that. We're taking 10 shots, and the chance that we make each one is 0.4. Now, what you're noticing here on this graph, it looks a little bit more symmetrical. And that's because, it's closer to being a 50-50 option. If it was 50-50, you'd get a perfectly symmetrical graph. And so here we go. Let's take a look at this. If we want to find our chance that he makes 8 or more, we can just set our minimum to 8 and our maximum to 10. And it looks like the chance that he makes 8, 9, or 10 of his shots is only about 1.2%. So not very likely. So for your homework, basically, this is what you're going to be doing. You're going to be given a situation. You're going to make a graph. I do want you to sketch that graph, just a quick sketch with some axes on there and the dots to make that graph. And then there'll be a question like, what's the probability that he makes 8 or more shots? And you'll answer it by using that cumulative probability. Or if it's just saying, what's the probability that he makes 4 of them? Well, you just click on it, and it's a 25% chance. Okay, one more little interesting question that's actually, why would we care about this stuff in real life? So we've got a scientist that proposes that a new drug is 70% effective. In a trial of 10 people, what is the probability that less than 5 are cured? And again, we're assuming that he's right, assuming that it's 70% effective. So we go into our graph here. I'm just going to change this one. We're still taking 10 people, but now it's 70% effective. And so you'll see our graph goes the other way now. It's pretty unlikely that if this thing is 70% effective, that only 2 people will be cured. It's pretty likely that if it's 70% effective, 7 or 8 or 6 or 9 people will be cured. But we want to know what's the probability of 5 or less. So 0 to 5. And it turns out that even if this thing actually was 70% effective, that there's still a 15% probability that in a trial of 10 people, this thing is only, or in our trial of 10 people, it's only going to cure 5 or less. And this is how drug companies actually test drugs like these. If they think that it has a 70% effective rate, they'll test it on a sample and they'll look at this kind of data. If it turns out that it only worked for 5 people, is that actually an unexpected outcome? And it turns out that it's not. 15% of the time, if you do this survey, even if the drug is 70% effective, only 5 or less people are going to be cured. Now, in real life, what we want to do is do way more. So if I did 100 people and 50 of them got better, that's the same proportion. Same exact proportion as before. But this time, the chance that happened is way, way, way less, almost nothing. And so if half the people got better out of 10, that doesn't really tell us anything. But if half the people got better out of 100, that says, well, there's a pretty good probability this drug actually doesn't have a 70% success rate. We might want to look at that some more. So that's binomial distributions. Here's your homework for this week. There's 4 questions. It actually goes over 4 pages just because of how big I made these graphs for you. If you're doing these on your own paper, just take the time to make some neat graphs. All you're doing here is taking your situation, using Desmos to make that binomial distribution. I want you to graph it, and then I want you to answer the question. What is the probability that you get at least 6 4s? And then the same thing all the way down. Put the thing into Desmos, sketch me a graph, answer the question. I have given you a little space here to make a table if you want. Might be helpful, might not, but for sure the graph and then answering the question there. Same thing here. Man, I stole my own problem off of there. You're in luck. That one's going to be pretty easy. And then your last one here, another example, make your graph, answer the question. Okay, this will probably be the last time that you hear from me before the end of the year. So just a couple of things. Remember, I've got office hours still Tuesday, which you're looking at this, the first day it's up would be today, Thursday. And then I'll also do office hours next Tuesday and next Thursday, the 26th and the 28th. This assignment is due the 26th. I need it in that day or before so that I can get everything graded and get your grades updated. That's also going to give you a chance if you want to go back and fix something. You'll still have time to go for those office hours and get things turned in. So I'll let you do a redo if you want after the 26th, but the first time you turn it in needs to be before the 26th. At that point also, I should be able to get your final grades up, and then you can decide if you want the pass or the grade. So far, I think everybody that's turning in homework is getting A's, I'm pretty sure. So you're definitely taking your grade, but you'd have that option at that point too. So stop by office hours if you need to, and otherwise have a great summer.